Okay, we are going to have an example right now to what we have studied up until this point. So we are going to have here in this example a solid circular post A, B, C, as you can see here. This is A, B, C. As we can see, it is like a shaft, for example, or a post, and it has different diameter. So we have diameter here, which is DAB, and another diameter or larger diameter underneath, which is DBC. Okay, supports a load P1, which is 2,500 pounds. This is P1, 2,500 pounds, acting at the top of the shaft, as we can see here, or this post. A second load P2 is uniformly distributed around the shelf at B. You can see here this load P2, it is distributed load, not concentrated load, and it is distributed around the shelf at point or at level B, or at this surface, because we have different diameters between the upper and lower part. So we have this shelf. The diameters of the upper and lower parts of the posts are DAB, which is 1.25 inches, and DBC, which is 2.25 inches. Okay, so we have the upper and lower diameter. This means that we can calculate the area of the upper post and we can calculate the area of the lower post as we know their diameters. Okay, there are two requirements here in this example. The first one is calculate the normal stress sigma AB, means that here we are talking about this cross section here at the post AB, or in this part, in the upper part of the post. This is requirement number 1. And the second requirement is if it is desired that the lower part of the post have the same compressive stress as the upper part. Okay, if we want the compressive stress in the lower part to be equal to the compressive stress in the upper part. Okay, what should be the magnitude of the load P2? Because here we have P2. So if we are going to calculate the compressive stresses on the second part, what is the load P2 that is going to be applied in order to have the same compressive stresses in the upper as the upper part? So the upper part is going to have only one load that is being applied on it, which is P1. The second part is going to have two loads, which is P1 plus P2. Okay, so we want to know how much P2 is going to be if we want to have the same stress. Take care, we want to have the same stress, which is stress AB equals to the stress for BC. This is the second requirement. Okay, so let's go and see how we are going to tackle the problem and how we can solve this problem. Okay, so first of all, as you can see here, just a second. Okay, as you can see here, we have P1, 2,500, the diameter of the upper part, 1.25 inch, the second diameter of, or the lower part diameter, DBC, is 2.25. Okay, first we are going straightforwardly. We are going to have the normal, or calculate the normal stress in part AB. It is going to be sigma AB equals to P1 over AB. A means the area here. And this area equals to pi over 4, the diameter squared. And P1, it is given already as we know, 2,500 pounds. If we calculate this, is going to give us 2040 pound per square inch. So this is the first requirement. From this first requirement, the stresses, what is the meaning of this 2040 psi? This means that the stresses, okay, here at the upper part is going to be, this is sigma AB equals to 20 40 psi, right? So in the second requirement, we want to get the same stress here for the part PC. We want it to equal to 2040 psi as well. Okay, this is what we want to have. So now we want to know how we are going to obtain the this P2 based on having the same stress as in the upper part. So simply what we are going to do is we're going to say this sigma BC, equals what? Exactly the summation of the two loads, P1 and P2. P1 plus P2, and then over the area of the lower part, which is ABC. This is the area of the lower part, right? Okay, so this is going to have what we are going to have here. P1, we know it, which is 2,500 pounds, plus P2, which is our unknown, we do not know it, over the area, which is pi over 4, 2.25 inch squared. And then we are going to equate it with the same stress as in the upper part, okay, 2040. Okay, this is one equation in one unknown, and then we can solve for P2, and then we can obtain P2 to be 5,600 pounds. So this is how much P2, or what is the magnitude for P2, in order to have the same stress at the bottom or at the lower part of this post or shaft. Okay, so this is the very simple, straightforward way for obtaining or solving this problem. There is an alternate solution for this part, which is part B, which is going to be primarily based on, it is very similar actually to what we have done here, but it is going to be like dealing with diameters rather than the areas, as we can see here. So I'm going through it quickly. So the stress BC equals to P1 plus P2 over the area, which is for BC, we know it will. So we're going to substitute with the diameter here, d squared BC. And then the stress at the upper part, sigma AB, equals to P1 over the area of the upper post, equal to P1 over pi 4 d squared for AB. And we need both to be equal, right? So we're going to equate this part with this part. The right hand side in every equation, we're going to equate it with them. So we're going to have this P1 plus P2 over dBc squared equals to P1 over d squared AB, right? We already canceled this pi over 4 in each case, right? Let me clean everything here. Okay, so we have this way. This means what? In this equation, we're going to have a relation between P2 and P1 in terms of the diameters of the upper and lower part. That's it. So we're going to have P2 equal to P1 times, after rearrangement of this equation, it would equal to P2 equal to P1 times the brackets here, dBc over dAB squared minus 1. That's it for this equation. And this ratio, we know it already because we know dBc and dAB. Okay, this ratio equals to 1.8. This means that P2 would equal to P1 times 1.8 squared minus 1. That's it. And then we can obtain P2, and it is going to be the same as we obtained from the first solution for part B. Okay, so they are going to be the same. Okay, this is for this example. I hope that it clarifies some part related to the stresses in each part, especially whenever that we are having different areas. Okay, thank you.